want to have one of these. When you're talking about light, we're talking about light today. And you'll want to have one of these, because you know what this is. See that water down there? See that water is nice and still? Watch this. What did I make? Waves. And you guys can see the waves. And if I dip it like this, are the waves close together or far apart? How about I go like this? So I can just shake this stick and touch the water and I can make waves, can't I? Is that mysterious? Is that understandable? No hassle. Now let's suppose I take this and I charge it up. Rubber rod, cat's fur. It's all charged, right? What happens when I shake it back and forth? What do I make? Begin with W. Wave, that's right. What kind of waves? Electromagnetic waves, that's right. In fact, I can't shake this back and forth without making electromagnetic waves. Right now, the electric field. You know, in the college book, I talk about electricity and magnetism first. And I talk about light. In the high school book, we do light first to get more with the phenomena that kids are used to and put the electricity, which is more abstract, further away. But really, it's nice to follow light up with electromagnetic induction. And here I am, I'm changing the electric field, and I can't change that electric field without generating a magnetic field. The magnetic field changes, that generates an electric, et cetera, et cetera, et cetera, et cetera, and there you go, and you've got light. And it turns out the speed at which that generation takes place is important. As the wave moves out, as the field moves out, if it moves too fast, then the electric field will induce a magnetic field with more energy, and that can't be. If it moves too slow, the energy would die out. That can't be. But there's one speed at which these waves can regenerate each other, in which energy is neither created nor destroyed. And that's the speed of light. And it was Maxwell that discovered that. And when Maxwell discovered that, story is, I think it's in the textbook, where he's walking with his lady friend that evening, and she's remarking about the stars in the sky and how beautiful they are. And he said to her, what would you say if I told you that you were walking with the only human being in all of recorded history who knows what that starlight is? She says, I would be impressed. She married him. It's James Clerk Maxwell. Yeah, because he found out what light was. What is light? Light is electromagnetic waves. Shaking electrons, shaking charges. Can't shake without making waves in space. And those waves are what we study now. And there's a narrow, narrow band of those waves that we call visible light, and that's the light that we're familiar with. So again, we talked before about things glowing. Things glow because charged particles are jiggling. They're vibrating. And the vibrating charged particles emit waves. Quite wonderful. So that's what we'll talk about today. We want to know how waves get through glass. How else could you explain it without using Newton's balls? How does light get through glass? And when light goes through glass, it slows down, doesn't it? And when light comes out the other side, what's it do? Speeds up. That bothered me when I first learned about that. First of all, I learned that the speed of light was a constant. Relativity. I get some ideas of relativity first. The speed of light's a constant, okay? In free space. That's the key, in free space. And then you start to study about light, and you find out that light slows down when it goes through glass. And the measure of how much it slows down is what you're talking about when you use indices of refraction. Okay? So how can light slow down? Einstein said it wouldn't. But the light between the atoms has the speed that Einstein was talking about, or the speed that Maxwell was talking about, 3 times 10 to the 8th meters per second. From atom to atom, our model of light now is that the light has one speed and one speed only in free space. So how can it slow down going through glass or water? Why do we have an average speed that's different than an instantaneous speed? And I think with these, we can kind of show that. And we'll also have to invoke the photon model. Thinking of light as little throbbing sparks of electromagnetic energy. That little throbbing spark would be called a photon. Vibrating quickly, maybe a violet photon. Vibrating slowly, a red photon. Even more slowly, an infrared below the threshold of seeing. And if it matches the frequency at which I didn't talk about resonance. You guys are hip to resonance. If it resonates with the molecules of the cells in your skin, they'll start jiggling too. And you say, ooh, it feels warm. And what's happening? The infrared is resonating with the cells of your body. And so you talk about a heat lamp. And when that resonance occurs, things jiggle. In fact, I used to be bothered by this. Why is it that ultraviolet light can't get through glass? It turns out that the electron oscillators making up the glass atoms have a resonant frequency that matches that of ultraviolet light. So at first I thought, well, that's the light that should get through. It resonates and passes along. But looking more into the model, we find out, no. If it resonates, that's not so good. If it resonates, those electrons really start jangling, whop, 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 and interact with neighboring atoms. And so what happens is it gets smudged and things start jiggling faster, the atoms themselves, and the energy then turns into what we call heat, thermal energy, just moves the atoms. So when there's a great match between the frequency of the photon coming in and the material, the light is absorbed, not transmitted. But if it's below that frequency, it can get through. Here we have a piece of glass. And we have different atoms in the glass. Now, photon will come in and impart its energy to the glass. Watch. This one that comes out is different than this one that comes in. And that's the way I look at light going through glass. When light hits glass, the photon that hits the glass, it's coming in, wow, 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 boom, hits the glass, it's dead. An atom in the glass, electrons start shaking up and down, and what do we have here now? Now that's an oscillator. What's that do? According to Maxwell, that emits a wave. Whoom, to the next one, to the next, to the next, to the next, to the next. And you get a cascading through here, and finally at the end here, another photon, indistinguishable, pops out the other side. Let's suppose you had an experiment where you had a tree, and you had a high-powered rifle, and you fire a rifle bullet right through the tree. And the rifle bullet hits the tree, slows down, and then comes out just as fast as it hit over here. Okay?
No.
That's not okay?
No.
And if that happened, would you say this has got to be a trick?
No.
And wouldn't you suspect if that happened, maybe the bullet that came in is not the same bullet that comes out in disguise? Maybe it's been sitting here all the time, and this one just triggers that one going out? Well, that's the way I look at light. So the photon that ejects out the other side is not the photon that came in and hit the first side. So you got glasses on? Guess where the light that you see is coming from with those glasses?
The inside layer.
It's being ejected by the inside layer of the glass. Now, if you don't believe that, take your glasses off for a minute. See how fuzzy everything is? Hey, but not the glass. You know, you're at a party and you're looking out and someone's looking out the window and they say, you know, it's really wonderful. I'm getting into science and everything, and it's just wonderful to think that, you know, I used to think I wasn't special, but now I know I am special because not understanding physics makes me realize how special I am. You say, what are you talking about, man? Well, look, see the starlight up there? The photons left those stars before the sun even came to be. And what were those photons for? They came all through space for eons and eons and eons, and boom, popped right through the glass, come through the other side, and boom, went right into my eye. That's my photon. Whew, I gotta count. And you say to your friend,
Sorry.
where did the photon come from that causes you to say there's a star there? Where's the photon in the end of the chain? Where does it originate? Check your neighbor. How many say no? According to my way of thinking, a photon left that star, went through eons, went through the glass, burrowed in, got into the middle of my eye, and bam, slammed against the retina. And honey, that's the way I see. Stand up. Let's hear some other answers. Next to the back row. Oh, oh my God.
We think the lens or the vitreous humor within the eye itself.
Ah, the vitreous humor of the eye. Fantastic, fantastic. Yeah, it's not the glass, is it? And it cascades, cascades. So everything you see is ejected by what? It's all in your head. Yeah, everything you see is all in your head. It's only the outside that stimulates what's in your head to then cascade to the brain. Yeah, the vitreous humor of your eye. Some people think that light, in fact, I had a friend that thinks that light is like everything else, really conscious. And I can show you that. Light knows ahead of time what's going on. You have a Polaroid, brighter here, not so bright here. And what this Polaroid is, it's just like the analogy we have in our textbook about the fence. Light coming through a fence. If I have a picket fence like this, I can take a wave and I can shake a rope, say, and the rope vibration will go right through the pickets, won't it? And if I shake like this, it kind of gets jumbled and stuck, doesn't it? Well, it turns out this is like a picket fence. This is like a microscopic picket fence. And it allows light to vibrate in one direction. Take a rope and shake it like this. How's the wave travel?
Up and down.
Up and down, up and down. Take the rope and shake it like this. It travels like that. Take the rope and shake it like this. It travels like that. When it's traveling like that, plane wave, I could talk about a vertical component and a horizontal component, couldn't I? Okay. Well, let's consider, instead of shaking a rope up and down, let's suppose I take an electron in an atom. Let's look at microscopically. It's shaking like this. What's the electron do? It emits a wave that's like that, transverse. And if it's going like this, it emits a wave like this. The direction of the plane of polarization is identical to the direction of the plane of the vibrating electron. Makes sense. Nothing mysterious follows. So over here, I just have like a picket fence that's going to allow those vibrations to come through. The Polaroid's not marked, so I have no idea what the plane is. The axis, I should say, the axis by which the waves will come through. But I can take another one, identical one, and I can plunk it on here, and you can see that what? They must be aligned. So what gets through here, gets through here. We're familiar with that. And your kids are probably familiar with that, maybe even ninth graders. And now if I rotate it, and so we've cut the light out. It's opaque. Now, HC, how come? Well, what gets through one plane, one filter, over here will block it if it's at 90 degrees. Take a third Polaroid and put it on the top. Oh, that's strange. I thought with 3 Polaroids, light would come through. Oh. Well, let's put it on the bottom. Oh. Well, let's put it in the middle. Oh. Oh. How can be? How can be? Well, my friend Gary Zukav wrote a book called The Dancing Woolly Masters, and his explanation was that the light, he didn't know about polarization, but the light would know what's ahead and adjust itself so it could get through. And the fact that the light would get through this combination was evidence that light is indeed conscious. And he's got about maybe 3 or 4 pages explaining that. And I showed Gary how it worked with vectors, and he was a little disturbed. Oh, is it that simple, he said? Okay, yeah, even if the light were unconscious, Gary, it would still work. And, and to explain this, this is a beautiful example of vectors. We talked about sailboats sailing into the wind, a beautiful example of vectors. This is another one. Because how are you going to explain this without vectors? So let's take a little quick look as to how that can be. Suppose we have one Polaroid like this, another one like this, another one like this. These are the axes of the polarization axis of the Polaroid. And in fact, light would get through if it's vibrating like this. And this one would be midway between. So these are sandwiched. I've got them 1, 2, 3. They'd really be this one, this underneath, and this underneath, as you saw over there. Well, let's suppose some light over here. Can't you say that's a depiction of non-polarized light coming at you, vibrating in every direction? In fact, you don't really have to put it like that. This would be sufficient. Because all those other ones could be resolved into vertical and horizontal components. And I make this one vertical just to line up with this. When this light falls upon this, what happens? It falls upon that. Whoom, okay. And what gets through? Only this one. So the only thing that survives is this. Maybe make these different color. You get the idea. What gets through is this. This light falls upon here. Can any of this light get through there? Yes. We could draw components. Here's a component here. Here's a component here, say, like that. This one doesn't get through. This component does get through. So what comes through is this. This is smaller than this. This is less intense than this. And that light falls upon here. Can any of that light get through? Yes. This one doesn't. This one does. So what gets through is that. How would polarizers be? How would sunglasses be oriented? Which would you use for driving along the road? Well, it turns out that when light reflects from a surface, it'll reflect in such a way as to reflect the component like that. Analogy, you want to skip some rocks across the water? You get some flat rocks? How about you throw the rock like this? What happens? Sinks. Let's suppose you throw the rock like this. It'll skip, 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 skip. And light's the same way. The components of light that come down like this will bounce off. The components of light like this will be transmitted and refracted. So there's a selective reflection to vectors that are parallel to the surface. So when you're driving down the highway, the light that comes at you is vibrating like this, and so you block it with which one? How about this one? No, you block it with these. Okay? And what do we use these for? Well, you're driving down the highway, and maybe there's a road surface there, and there's a great big silo. So while the road surface is there, you drive like this. When you see the silo, you go like that. You switch eyes. No, I'm kidding. You use these for 3D glasses, and that's a whole other topic. And the text talks about it, about how one eye can see one view and the other guy can see the other view independently, and that's really nice. Here's a next time question that you could give to your kids. And this is a real puzzler. Let it stay there for about a week before you give the answer. But again, if you tease them, and then you can show an answer the week later and leave that in the bulletin board. We'll lecture and they'll take notes, but oftentimes their notes aren't very accurate. If they have this on the board or posted somewhere, then they can study it and maybe get the idea. Here at this point, I'm avoiding the idea that the intensity of light is proportional to the square of the vector. Now we want to talk about next chapter. Electrons in the sun. Static or jiggling? They're jiggling around. When they're jiggling around, they can't do that unless they emit radiation. And they do. And so we get light from the sun. Because the jigglings there, million billion vibes per second, those jigglings correspond to the optical part of our eye, which you can pick those up. So we might get something like this. This is a radiation curve. Brightness for sunlight versus frequency. I stress frequency. I try to stay with one idea rather than shift between frequency, wavelength, wavelength, frequency. I tend to stay on frequency. And I think by doing that, we have less mix-up. Most textbooks will emphasize wavelength. I think frequency is the primary thing. So I stay with frequency. And we'll get something maybe from the sun, something like this, which is to say there will be not very bright light at low frequencies and not very bright light at super high frequencies. Most of the brightness of the sun is at a frequency which is right about here. And that'd be the peak frequency right there, and there'd be a particular value down here. Does anyone know what that value would be in terms of color we see? Yellow. The same color as tennis balls and fire engines. Sort of a yellow, oh, there it is right there. I see it with the corner of my eye, a yellowish green. And that's the brightest light that we can see. That's the brightest light we can see. That turns out to be the brightest light that the sun emits. And that kind of fits together, doesn't it? Where did we evolve? Aren't we in the solar system? Don't we look at the sun? Isn't the sun the source of our light? And it turns out, there it is. It's sort of a yellow-green. And then it turns out that down in here, we can't see anything, infrared. I should have prefaced this by saying, if we take a piece of metal, maybe wrap some wire around it and heat it up in a dark, dark room. Before we start to heat it up, with the room completely darkened, nobody can see this. But as we start to heat it, the glow that it's giving all the time becomes more intense and the frequencies increase. And pretty soon we start to see it. And what color do we see? Red. We see red. And red is the lowest frequencies that we can see. And as we continue to heat it, it gets a little bit more orange, yellowish, and then it turns, wow, does it turn green for us? No, it doesn't. And it doesn't turn all the colors of the spectrum. It seems to go red to white, and then if we could continue heating, it would melt, vaporize. But if we could take the gas and keep it there and continue to heat it, pretty soon all of a sudden it would turn blue, bluish violet. Then if we continued heating it, pretty soon we wouldn't see it at all. Now what would happen is the distribution would be so far away from where we can see, it would be invisible. We'd call it an X-ray emitter, a gamma ray emitter, but maybe not visible light anymore. But anyway, for our sun, the temperature of our sun is such that, remember we talked before about peak frequency of electromagnetic radiation directly proportional to the absolute temperature? The temperature of our sun is such that our peak frequency hits right in the yellow-green part of the spectrum. And down here we can't see it, and it turns out we can't see what's going on up here. We start here with red, go to violet, and beyond. We don't say beyond violet. What do we say, gang? Ultraviolet. More pizzazz. We don't say below red. What do we say in science? Infrared. More pizzazz. So we got the infrared down here, and now we have the colors. So we get red, orange, yellow, green, blue, violet. And with that, the 7 colors is really made up, because they could have had 8, could have had 9. In fact, Newton put in the color indigo so we could make it 7. There was something magic about 7 in those days. But we can actually, what are our eyes busted up into? Our eyes busted up into 3. Our eyes can only see 3 colors. The cones in our eye. They can see the middle frequencies, and they can see the lower frequencies and the high. And these look to our eyes to be red. These look to our eyes to be green. And these frequencies average out to be blue. That would include violet, low blue. Green would be blue and yellowish. And red would be that, and orange. And just those 3 will do. And with those 3 colors, we see everything that we see. Our color television sets are what 3 colors? Red, green, and blue, period. And now we're going to see a little color show by Jim Redmond. To demonstrate what we just talked about, Jim brought in 3 lamps. And then we're going to need a volunteer. Peter, you're going to be our model.
You betcha.
All right?
Over the years, one of the problems that I've found with kids is they don't believe that white light has all the colors in it sometimes, so this is a good way to kind of prove it. But we can adjust, the nice thing about the rheostat is you can adjust these things. Okay, green light and blue.
Let's put all 3 on at once and see what color they overlap to be.
Full intensity on. And
That's about as white as I've ever seen. What'll happen if I turn this one off?
Okay. There you go.
Ooh.
Yellow.
Now, Peter, could you show us that your shirt will still be the same color under these 3 lamps? Yes, yes, yes.
Behind it.
Can you guys explain all those colors? Let's do them one at a time.
There's the red. And his shadow is? Black. Black. Okay.
Now I'll put another lamp on and we'll illuminate that black shadow with green light. It turned green. See the shadow from the blue, see the green lamp? The shadow from the green lamp will now be red when red light shines on it. Ain't that nice? Why? Well, there's okay. There's a shadow of Peter on the wall. All right, now if we shine some, let's try some blue light. Let's suppose we shine some blue light on that dark shadow. What color will the shadow be? Blue. Okay, now to understand all those colors, let's just look at this. No problem that the shadow's dark. If I shine green light on it, it'll turn green. But now I have a shadow from the green light, and why is it red? Because the red light's on it, that's why. So that one's so far so good, huh, gang? Now look at the yellow background. What'll happen if I shine blue light all over the yellow background? White. But the blue shadow, blue gives a shadow over there that's yellow. Now why is it yellow? I got no yellow lamp up here. Check your neighbor. Why is the shadow on the left yellow? How many people are going to take the bother to do this demo with your kids? Yay. How many? Everyone that's not, stand up. I want to see what you look like. Okay. Quick and dirty, why the sky is blue. Sun up above. Electrons vibrating like mad, showering out light that comes down to the earth. The light comes down and hits the Earth's atmosphere. And what's the Earth's atmosphere consisting of? Molecules, atoms, mostly nitrogen, oxygen, molecules, big or small? Small. Small, very good. Okay. When that light comes down and hits, it rings them like little bells. Think of the little atoms in the sky as being little optical tuning forks or little bells. And little tiny bells ring at what? High frequencies or low frequencies? And we can show that with a demonstration. Because what do we want to do? We want to all the time put knowledge on top of knowledge, give new knowledge based upon old knowledge. You see these 2 strings hanging from the ceiling here? See this one with a little tiny bell? Can you see that? And you see this one over here with a great big bell? Now what I'm going to do is I'm going to ring those bells. And when I ring those bells, you predict, when I hit this bell, high frequency or low? Boom! Now I get the big bell. Ding! Right? Right? Does that feel right? No. That doesn't feel right, does it? That feels bad. It's the other way around, isn't it? The little tiny bell, bing, at high frequency, and the big bell, boom, 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 boom. So we have little bells in the sky. And when the light comes down and hits, boom, it makes them ring too. And the little tiny molecules ring at a frequency that we see as blue light, violet and blue. If the bells were bigger, or clumps of bells, maybe a lower frequency. So what we find is we find these bells are just scattering all over this blue light. We look up and we see, hey, wow, isn't that nice? The sky is blue. And it looks a really bright blue because it's got a very, very dark background. And if you have a dark background, you see that blue. By the way, when you're looking at distant mountains, and there's a lot of sky between you and the mountains are dark, what color do the mountains look? Blue. Is it the mountains that are blue? No, you're looking at the blue sky between you and the mountain. I remember when I was a kid, the art teacher was telling me to make the distant mountains look violet, for example, violet and bluish, huh? And I said, why? Why would they look that color? She said, because they're far away. And there we go, see? And that's what it was. I didn't know that then. But that's the sky you're looking at. You're looking at the sky between you and the mountain. Now, sometimes we look at sunset and we find the sun turns from a white or yellowish white, huh? Yellowish white to what when it gets down low? Red. Why would it be red? And what happens? At that time, we have the sunlight going through much, much more air, huh? Through much, much more air, huh? Is the Earth right here? Okay. And here you are standing here. And here's all the sky molecules. Greatly exaggerated here, isn't it? So when the sun's directly overhead, it doesn't have to come through much light, through much atmosphere before it gets to you, right? But how about when the sun is low in the sky? Look at the light now. The light has to go through. Look at all that air the light has to pass through. And as the light is passing through that air, what color is being scattered? Blue. So the blues are being scattered, and everyone over here is saying, oh, look at the blue sky up there. They're looking at the light that was meant for who? For you, okay? Because here you are right here, and you're looking that way. But it turns out by the time the light gets to you, how much blue is there? A lot or a little? Begins with an L. You got it, okay? So very, very little blue light is there left for you to see. So with all that blue scattered off, honey, you get the leftover. And if you take white light, if Jim had taken his lamps over there and put all his lamps on and turned off the blue, what would be left? Yellow. Check your neighbor. Begins with a Y, rhymes with mellow. And then if he turned down some of the green too, what would it turn? Begins with an R, rhymes with Fred. Red. And what color is the sun when you filter it all out? And you want to see a nice application of that? I'll show you a nice application of that. When's the last time you guys have seen an eclipse of the moon? And what color was the moon in the shadow? Could you see the moon in the shadow? Son of a gun, you could see it. And you can see it. And what color did it look? Do you remember? Reddish. How come reddish? How come the lunar eclipse oftentimes looks reddish? Especially if it's right in the middle. What does this reddish color have to do with the sunsets all over the world? During a lunar eclipse, light from the sun grazes the Earth's atmosphere, which acts like a lens to refract the light onto the otherwise dark moon. Only the low frequencies traverse the long path, so the light to fall on the moon is red and orange light refracted by the sunsets a full 360 degrees all around the world. So if you're standing right here, for example, here you are standing here, and you're looking out, and you're looking out at you're looking out this way. You're looking toward that sun, and that sunlight's coming just like this. Just go like this. Whoop. The light continues. But that light to get to you has traveled through what? All those kilometers of air, and it's got really reddish, hasn't it? Now you move your head and let it keep going by. It's going to move through as much going out this way. And boy, you're going to strain out almost everything. And so what you get at the end, coming through both of these, is really, really red. So you get a nice deep red over here. Copper red. Ain't that neat? Kind of poetic. Here you have some light coming down, bouncing off some water in the street. Let's suppose it's blue light. Blue light comes down, boom, reflects. What color do you see up here? Blue. I have a blue shirt on. If I looked at my mirror image, what would the color be? What if I had a low frequency shirt on, red? What would the image look like? Red, very good. It turns out that frequency doesn't change when things reflect, when light reflects, right? So we see blue. But let's suppose now we have a water surface down here and a gasoline surface on the top. Some of the light reflects off here, but some goes down here and comes up. And maybe this extra distance is enough to cancel out. You hip that a wave like this and another wave on top of it will combine to give me a wave of increased amplitude. And you hip that if we have a wave like this and have another one start and say right here, I'll get no amplitude. This is destructive interference. This is constructive interference. Well, over here, what do I got? Am I going to see my blue light? No. So the eye's not going to see blue. So what's it going to see? Whatever's left. Nothing. But let's suppose instead of having blue light come down, let's suppose I have sunlight. If sunlight illuminates this, this is just the right thickness to cancel blue. If I make it a little thicker, it might cancel green. Make it a little thicker, it might cancel red. But what it'll do, it'll cancel blue here. So if white light's coming down, one frequency doesn't make it, and that's the blue. And when you take the blue out, what do you get? You get yellow. You see yellow. An interesting thing on interference colors that I didn't know until somewhat recently. When you see those interference colors, gasoline on a wet street and everything, notice that you won't see them as reds and blues and greens. You'll see them as the subtractive primaries. You'll see magentas, yellows, and cyans, Check that, and that's what you get. So the colors you see by interference are the subtractive primaries. Interesting. You'll never see a bright red coming from the ray or a bright green. Always the subtractive primaries. So you really are seeing the color by subtractive, by destructive interference. Sometimes interference is presented as constructive interference, in which case then you ought to see the reds and the greens and the blues. But the colors you see are the result of subtraction of colors. You guys all hip to the idea, how big does a mirror have to be to see a full-length image? How many people are already familiar with that question? How many? Oh, there's a lot that aren't. Oh, that means a lot of people will get this wrong. Is it okay to be wrong sometimes? Is it okay to fall down when you're roller skating? Yes. To see more of her head in the mirror, she should hold the mirror closer, farther away, or makes no difference?
Or a smaller head.
Or a smaller head, yeah. Check your neighbor in that. Check your neighbor. If you have a mirror, try it right now. How many say needs a bigger mirror? Not everybody. Okay. That's a toughie. What you do is you assign for homework. If you stand in front of a mirror, you want to look at your image, and let's suppose you stand one body length away. What's the smallest the mirror can be to see all of yourself? It's very, very controversial. You get my students might end up fighting about it because they won't believe it. Especially they won't believe, then when you figure it out, it turns out to be half size. How would it be if you get further away? Can you use a smaller mirror? Nope. And the answer is invariably yes. But the answer, of course, is... And when you give your explanation about that, here's one idea that you might have. Here's a couple of twin people here, twin students. And there's a wall between them. And we want to cut a window in the wall so that they can both see each other. Let's suppose I cut the window this big. Can this twin over here look and see all of his brother there? No, he can't. In fact, how big could the opening be so that this person could see the toes? Well, all you do is you just draw straight lines. You could do that. This person wants to see the toes. Line of sight would come right in there. In fact, if this person wants to see this guy's toes, line of sight would come right in there. Wants to see the top of the head, would look like this. He wants to see the top of this brother's head, it'd look like this. Looks like, gang, what you can do is you can cut away this part right in here. And each person will see all of these themselves. So it turns out this is halfway down, halfway up. Turns out this is half size. If these are 6 feet people, a 3-foot opening would work. Now how about distance? Then you could draw the people further away. This one gets further away over here. Well, this guy's going to get further away over here. And what do you have now? This fellow wants to look at the toes. What's he do? Looks right down through the same opening. Wants to look at the top of the head. Same opening will do. And this way, and this way. And so it turns out it's independent of distance. So no matter what distance, as long as they're equal on both sides, that opening will suffice. In the same way, a plane mirror will give you the same thing, but now light being reflected. Fantastic. This is very, very controversial. And the reason it's controversial is people think that, well, I know I can take a small mirror like this and I can hold it up and I can see Grouse Mountain in it. I can see the bottom of Grouse Mountain, I can see the top. That's not the question we're asking. We're asking, how big does a mirror have to be to see you? You go up in Grouse Mountain and look in here and see if you can see all of yourself. You can't, okay? So I can look in there and see all of you guys here, but to see myself, which is the question being asked, and which is oftentimes not the question being answered, that's the little distinction thing we were talking about, And therein lies your problem. So you'll have fun with this with your students in class. You'll have a lot of fun because it's going to be counterintuitive. And what you can have is you can have them stand in front. In fact, I invite you tonight when you go home, look at yourself in the mirror, put a mark where you see the top of your head, put a mark where you see the bottom of your beard. Isn't that right, Karen? All right? And then you move back, and son of a gun, guess what? You keep moving back, 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 back. Oh, but nope, you've got to line it up so you get the top of your head, and son of a gun, the bottom of your beard's in the same place. Makes no difference if your chin, okay, chin, beard. It makes no difference near or far. This is controversial, it's fun, and the students are enlightened, hopefully. And then from that, then we want to get into refraction. We want to distinguish reflection from refraction. Oh, there's interesting questions you can get with this too. Let's try one before I get into refraction. She takes a photograph of a friend standing on the bridge. Which of the two sketches more accurately shows the photograph of the bridge and its reflection? Do you see a difference in these two, gang? Do you see a difference? What's the difference? Notice that this shows the underside of the bridge. This doesn't. This reflection here is just a fold down of what's on the top, which most people think is the case. Most people think that the image is just the top folded down. In fact, many people who take photographs, when they want to get a photograph of a nice image and a nice still lake, get frustrated with the ripples in the lake and instead dummy it up in the darkroom and just take the top part and fold it down and shoot it and expose it just right and give you a photograph. You say, oh my God, what a beautiful photo. Many are phony. Many are phony because it turns out the reflected image is not this. It's this, taken from a different angle. Did you guys read that? Where she is, put her upside down so she's right here, and now have her look, and that's what you see. So she sees the mirror image as if viewed with her beneath the water as far as she is above. I'll give you an example. Here's a stool. I look at the stool. I see a view of the stool. Now I take a mirror, and I put a mirror on the floor. And now I see the stool, and I see a mirror image of the stool. What do I see in the mirror image? Bubble gum. Stuck to the bottom of the stool. So what I'm seeing in my mirror is not what I'm seeing up here. Or it could be a rock with maybe a frog right in the middle. And I look at the mirror image and what? There's no frog because the light is coming up looking like this. So again, another illustration where you as a physics teacher are helping people to look and see what's there meaningfully. There's a canoe in the water. Here's a person sitting in the canoe, okay? Now the mirror image, how about the mirror image like this? Are you looking, here you're looking down into the boat. Are you looking down into the boat in the mirror image? No, the mirror image would be sort of like this, even, like this, just around like that, one shape. You wouldn't be looking down at all. Or you're looking at mountains far away. And way back here, way in the back, okay? It's a high one, but it's way back. And here's a lake. We have a tree over here, okay? We have a little house over here, whatever, okay? Now we got a nice lake over here, lakefront, and we want to see the image, huh? Let's suppose the image is something like this. So far, so good. Mountain peak. Okay. So far, so good. Distant mountain. Where did I make my mistake? You probably don't see the distant mountain. it's probably not even seen. Because down here in the water you look up and whew, from this point of view, you don't see it from here. But from up here you do. So when you see something that's in the distance and it lines up all in here with here, boom, tilt, phony, phony. Someone's done some darkroom magic. Watch for that. It's common. Refraction. Cartwheels rolling, top view, rolling along the sidewalk. Grass. Here's the cartwheels. Let me just draw this in the middle. Let me draw it with a different color pen. Black's good. This is the direction of my cartwheels. When the cartwheels encounter the grass, there's more interaction with the grass than there is with the sidewalk, so it slows down and the cartwheels will bend off course. Isn't that true? So they'll come down like this and they'll bend off like this. That's because this wheel slowed down before this one did. And the result of the bending is a result of a slower speed here than here. And if it slows down a lot, it'll bend more, approaching the normal. If it slows down a little, if it slows down not at all, it'll continue at one speed. If it slows down a little bit, it will turn. Well, light does the same thing. Waves of light coming from above. Waves of light hit and slow down, and they bend too. And what will happen in here is you'll find that your light will do much the same thing. Notice the wavelength is shorter here than here. What stays the same? The speed? Nope. The wavelength? Nope. The frequency? Yep. Hence I emphasize frequency. That stays the same. So the up and down vibration mode still is the same in here as here. So we find the light going at a slower speed. Why does it change for different colors? Why does light have different speeds for different colors? Well, we know that if we have ultraviolet light, boom, it's dead. But if we have blue light, we know it gets through kind of slowly, and red light gets through a little quicker, and green light in between, don't we? Well, I like to use an analogy like this. Let's suppose I'm a photon coming in here, boom, and I interact only once in a while with the people along here. I come along this, I miss you. Say, oh, hi, how are you? Nice to see you, Cecilia. Da, 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 da. Oh, hi, Susan. And I get over here. I'm through really quickly. I only interacted with 2 of the people. And that interaction with only a few allows me to have a greater average speed. Let's suppose I'm green light. Green light, I will interact with, it'll be closer to the resonance. I come over here. So, yeah, man, I do, man. Okay. Cecilia, I do that, honey. Da, da, da. I'll get through a little faster. And let's suppose I interact with all the people as I go. Blue light. And what will happen, it'll take a long time to get to the other end. So different colors of light will have different speeds in a transparent material. Different colors of light have different frequencies. Different frequencies have different interactions. They interact more or less often, depending upon how close they are to the resonance. When they get closer to the resonance, they interact more often, slower light. This is all talked about in the text. And apart from the resonance, interact only fewer times, and therefore get through at different speeds. So we find out, that being the case, we can get such things as rainbows. We can get spectra with prisms. You guys know that if I have some white light coming up here, that white will come up and will bend, and maybe it'll bend like this, and then bend over here like this. And another color might bend more, bend like that. Another color might bend even more, like blue, and come like that. And I can separate my white light, which is a mixture of all the colors, all the frequencies, and I can get here red, and say green, and blue. And I can shine this on a screen, and I can say I have a spectrum where I have the whole rainbow. I've only taken 3 sample rays. But here we see a greater slowdown, more interactions, a greater refraction. I don't even use the term index of refraction, which is just a ratio of how fast it would go out here in a vacuum, say, as to how much how fast it would go in here. I don't even use it. I always emphasize the idea that light slows down when it goes from one medium to another if the interactions are different in the two mediums. And that's what you are talking about when you say different indices. So there's a prism, and we can describe that, and kids are familiar with it. They see it on album covers and that sort of thing. It's sort of classic. There's nothing new. Now let's suppose we have the light coming like this. Light's coming up here, hits the prism, and comes down here, and you have an observer over here. Does this observer over here see that splaying of light? Answer begins with the N. No. No, very good. But let's suppose you put a mirror over here. Now the light would come down and would reflect. That misses. And it goes right in the eye, and this misses. So the person over here is going to see one of those colors because the light has been refracted and reflected. And the person's in just the right position to see one of the colors. What am I leading into, gang? Rainbows. Rainbows act much the same way. Instead of having a prism, you just have a round drop. And the light in the round drop refract in, reflect, and come here. It's not drawn very well. In fact, I have a model of that right here. White light comes in, hits my drop, refracts, reflects. Some comes out here. Some reflects, comes out here, and there the eye then can see one of those colors. It looks like this case, the eye will see green, yeah? Would you say in this particular case, the eye will be seeing green?
That's a blue and a red we got there, right?
See, this is red color, blue color. Guess what's in between? Begins with a G and is Irish. Green, very good, okay? So now the light's going to see green. It turns out to see red, this would be 42 degrees. To see blue, it'd be 40 degrees. And it turns out every raindrop in the sky is dispersing light into really a cone. Think of this, guys. Light's coming from here, okay? Let's suppose the sun's out there. The sun's coming, hitting a raindrop. Here's a raindrop. Here's the sunlight coming in. But you know what? It's hitting a whole, every raindrop is dispersing a cone of light. Can you see that? These are just arrows. These are just rays, two rays, but there's a whole three-dimensional array here. And so it's like I have a cone here, a cone shape. When I look down here, I see the red. I look over here, I see the blue, but I see it all the way around there, keeping my sunlight the same. Okay, so every drop sends out a cone shape. Now, we want to view the rainbow. Can I have a couple of volunteers? New volunteers. Karen, you stood up? Yes. What I'm going to have you do, Karen, is I'm going to have you sit over here. Sit right there. All right, Karen, what we're going to do is see the sun out there, honey? See? It's getting towards sunset. By the way, you see rainbows either early in the morning or late in the afternoon. You don't see them at noontime. Noontime's coming like that, and here we go. You'd have to be up there to see it. Isn't that nice? See? So you're going to see it when it's low in the sky. So here's the sunlight coming in, okay, hitting a drop over here. Now Karen's sitting here. Karen, turn around a little bit. Okay, a little closer now. What I want you to do, at the risk of putting your eye out, put your eye. Oh gee whiz. I'll put it higher. Here we go. Put your eye right where the blue is. Now Karen sees blue. Whoops, it's got a little. Oh, sorry. Get him up. Okay, Karen sees blue right there, right? Okay. Now Karen. Okay, let go. Is Karen going to see blue light from a drop over here? Look, it won't reach her. It'll miss her. In fact, she won't see blue from a drop over here either. But she'll see. Now grab that blue, Karen. She'll see blue right there. And where else will she see blue? And the condition is that 40 degrees got to remain constant. So she'll see blue there. Hold on to it, Karen. Don't let go. She'll see blue there. Blue there. She's going to see blue keeping that white light parallel. And there's where Karen is going to see blue. Any mystery as to why she sees a blue shape, blue color? Any mystery to why over here it's nice and steady, and over here on the right side it will always be a little kind of strange? And now Karen's going to look to see red. Now I got a question for you, gang. Do the blue again, Karen. Will she look higher or lower in the sky to see red? And let me show you the sticks. And check your neighbor. Higher or lower in the sky to see a drop that will refract and reflect red. How many find out that the person sitting next to you is not saying anything? That's because that person maybe doesn't like you. I got him talking now. Don't accuse me of that. Okay, show of hands. How many people say Karen's got to look higher in the sky? Woo, wonderful. How many people say lower in the sky? Stand up. Karen's not there today. Okay, that's why I called you up here, Karen. Okay, now, Karen, to see a one higher in the sky, Karen's got to look up here. Get it? And there's where she sees the red. She sees one there. She sees one over here. See where she sees the red, gang? Any mystery as to why she sees a bow? Teresa, can you come up here? Teresa, you come over here. Okay. Now let's see for you. You want to look at the blue. Okay. Get a little closer. Teresa's a little shorter, so her bow's down here. So Teresa sees. Whoops.
Hard to do, I know.
No, let's do the red. Let's do the red. I get red ink here. Okay. A little higher. Okay. There we go. So Teresa sees her bow here. So if Karen says, Teresa, look at the wonderful rainbow, Karen would have to say, we'll move over and get over here. Thank you, Teresa. Thank you, Karen. Okay. And so here we see that everybody sees their own personal rainbow. Dig that. So you look out and say, well, look at the rainbow. Move over. Oh, yeah, okay. Over here you see a different one, a different one, different one. Then you start running on the street. Son of a gun, the thing's going with me. Then someone says, run to the edge and get the pot of gold. You run to the edge, and what's it do? It moves with you. So the rainbow, and the rainbow is extra bright if it's extra thick, because you're looking right down a cone. And if it's very, very thick, you'll see a vivid bow. If it's very, very thin, you'll see a faint bow. But why the bow shape? I had a lot of trouble for years trying to explain why the bow shape, and I think these little sticks do it. So you can make this yourself. Put a piece of styrofoam and just put some sticks in there. And make your 40 degrees and your 42 degrees, and there you are. Makes a nice little model. Oh, this was just made by the person in our department who makes things like this. Yeah. It's just a wooden ball, and he made it nicely. His name is Will Maynez. Will Maynez, he's a wonderful guy at City College, and he made this to specs, and he even thought about putting these little things so I could move around with it. Just a little screw eye in there. And so I can screw off and I can travel with it. And aren't these rainbow sticks nice? But you ought to make these up. You could make them up in your own department. I was on the island of Kauai in Hawaii. I took a helicopter ride and I wanted to see the full circle rainbows. And when I went up there, sure enough, in Kauai, there's almost always rainbows in the sky because it's always raining there. And went up there and the pilot says, if you look off to the right, you'll see a full circle rainbow. And there it was. And he said a sentence that I jotted down and is now in your book. And then he said, all rainbows are completely round. It's just that down there, the ground gets in the way. Yeah. Isn't that nice? That was worth the price of the flight itself. And look in the book. It says, all rainbows are perfectly round, but viewed from below, the ground cuts off the bottom part. And not only are they perfectly round, guess what's right in the middle? Your shadow. Your shadow. So when you're looking and you see the airplane, see the helicopter shadow, it'll move right along the mountains. You can see how fast you're going, and the rainbow's right around it. Question?
Yeah, how is it that we can see multiple rainbows at once?
Yeah, you'll see a secondary rainbow as well. And that secondary rainbow, covered in the text, and it's always dimmer or brighter? Dimmer. Dimmer because of what? A second reflection and a second refraction. The photographer wishes to photograph the rainbow. but is disappointed to find the camera's angle of view is not wide enough to see the whole bow. To get the whole bow, she would be better off if she were closer, further, or it makes no difference. Check your neighbor. Here we go, gang. Any full circle rainbow near or far subtends the same angle, twice 42 degrees, 84. So to photograph a full rainbow, whether a very close one produced by a handheld garden hose or 1 miles away, the camera's field of view must be at least 84 degrees, a very wide angle lens. Fisheye lens. And the lady says down below here, all rainbows, by the way, are completely round, as can be seen by a high-flying helicopter. Viewed from below, however, the ground gets in the way. To photograph a full circle rainbow from a helicopter, the 84-degree field of view must be vertical as well as horizontal. Has anyone successfully taken a photograph of a full circle rainbow? I could say about more than 10 years ago, the human race has not got to a point where any human being has taken a photograph of a full circle rainbow. I don't know if that's changed. But, you know, there's always a time. You know, there was a time airplanes didn't fly. And there was a time before that no one had ever photographed one. And to my knowledge at that time, I don't know if they've done it since, but no such thing exists. And gang, geez, we got other practice sheets that, delicious. Go through those. But no, I got some delicious homework for you today. You remember yesterday I neglected you? You felt bad about that? All right, not tonight. I got something nice for you. Keep you off the streets. Can you guys do 5? 5's kind of overload, isn't it? 5 questions? You would never give your students 5 questions. At lunch, ask me sometimes why there's at most 15 questions in the book and not more. And ask me at lunch why there's like 50 in the college book, but so few in the high school book, and I'll tell you. We only have a few. This is Think and Explain number 5. On page 441, do number 14. One, two, three, 4, 5. Can we do those? Write them up. Hand them in tomorrow morning and see how many you can get right. Let's look at the homework we had for last time. First homework had to do with, photons through the glass. Photon through the glass. How can the photon go through the glass, slow down, and then emerge on the other side at the speed it had before it hit the glass? And you said, how many people are writing this down for the first time? Stand up. All right. And how many people are ignoring this request, Jose? Okay, what did you guys say?
Not the same photon.
Different photon. Twin. Different photon. Okay, and that's about, then we could go a little further than that. Let's move on. Next question, we're on page 441, number 14. It had to do with the, red, white, and green ship sinks deep in the water. You're scuba diving. You're scuba diving, you take your flashlight and you shine your light on the ship. Does it look red, green, and white? Yes, it does. You're shining a flashlight on it. So no big deal. Next question. No. No, if it's illuminated by the sunlight up above, then what? What doesn't get down that far? The red. The red doesn't get down that far. So the light is absent in red. Will the green part look green? And what will the white part look? Green. Oh, cyan. Yeah, cyan green. Yeah, okay, yeah. In fact, you ever notice you take a white bathing suit and the deeper you swim, it starts to get greenish if you're just looking at your friends. Yeah. In fact, if one bleeds underneath, the blood looks what? Black. Yeah. Because there's no light to give you that nice red that you're used to looking at. And the next one was kind of a neat one, wasn't it? A little challenging, huh? The Coke bottle. Do you guys ever see a Coca-Cola bottle immersed in a piece of plastic? Well, let's see what happens there, gang. Here we have a top view of say a Coca-Cola bottle. We're talking about that example in the text. Well, let's take light from here. Light from here will reflect in all directions. Some light will go up this way, some this way, some this way, some this way, some this way. And when that light comes out, it'll hit the surface and then refract, won't it? Let's suppose our eye is down here. We're not interested in the light rays going this way. We're interested in the one that can get to us. And it turns out that might be one that's like this. And it will speed up and come right to our eye. So, we see, and the same thing happens over here. And this diagram, I believe, is in your book. And so we see the Coca-Cola as being like that. So it looks thicker. You get a root beer mug, and you see the mug. It looks like it comes right out to the edge. You're seeing refraction. Very thick glass, there might be very little in there indeed, but you see it to be bigger. And that's nice for marketing. Looks good. And it's an example of refraction. Now, let's suppose we put this in a glass block, in a plastic block like this. All right. Let's look and see what happens to this ray. This ray comes down. Does it bend as much? No. In fact, if this were the same, if light traveled as fast here as here, then it would just come through like that, wouldn't it? Right? But usually it travels a little bit slower in here than over here. So it might go like this, and that won't get to our eye. So what's going to get to our eye? Oh, I'm mixed up now myself. Ooh, I'm mixed up. Volunteer. Come on, Chris. All right.
So, you want to have a look at my diagram?
Nice to have teachers for students.
Does that look okay?
Let me see. Let me get my refractors. Oh yeah, if you had the same. Very good. That's nice.
So I just had the same index of refraction for both. So any light that comes from here travels straight through here. There'll be no refraction here either. There's none
That's
here
right.
because it's
That's
the
right.
same index of refraction. And the same thing for here, no refraction, but also I had some ray diagrams on the edge. So depending on where you put your eye, just get a bigger eye, yeah.
Big eye, yeah.
But everywhere there's no refraction, so you get to see the exact thickness of the
Yeah.
glass.
So there'd be no effect at all due to refraction for how much Coca-Cola is in the bottle if you had that case. Jim?
If the glass and the plastic were actually matched,
Yeah, and they are.
you wouldn't see the glass.
Yeah, that's right. You wouldn't even see the glass. Good point. You wouldn't even see the glass. And you know where you get that nice? If you take what is it? The syrup, the oil, Wesson corn oil. Wesson corn oil, light travels just as fast through that as through glass. Pyrex glass. Pyrex glass. Very good. So if you put a Pyrex glass in Wesson oil, you can't see it. When we see the interference rings, you look at gasoline on a wet street and you see they're all bands of color and the bands all link up again. And how is that analogous to a contour map? What's going on there? What do the different colors represent, gang? Different thicknesses, right. And you can follow that through and you can see the different thickness. And the last question on the homework was, if you're looking at something and through interference colors you see one color, say yellow, what will happen if you tip it? If you change the orientation at which the light's coming to you, what do you get then? A different color? You might have a case over here where this particular wave would cancel. But if you put your eye down here, so your line of sight is like this, then a longer wave would be the one that would cancel. And so you might get a particular color here. Say you're seeing yellow because blue has been canceled. Get down at a grazing angle, so there's a bigger path length. And the blue will no longer cancel because it's too long. So what will cancel is maybe a longer wave, like maybe a red. And now you rise up here and you say, oh, gee whiz, the yellow turned to a cyan. You see the complementary color of red. And again, the colors you see up here are the subtractive primaries, the magentas, the cyans, the yellows. Look at that. You see all that violet color. That's the magenta. But you get different grazing angles, so you can see different colors. You see that you take an abalone shell, you look at it and you turn it, you'll see different colors. That's what's going on there. Green filter on the bottom, red filter on the top. White candle. What color is the candle over here? Check your neighbor. And the little boy asked, what happens if the green filter is blocked so no light gets to the bottom half? Then what color is the image of the candle? Do you see all the candle? Yep. All of the candle? Yep. Every bit of the candle? Yep. You mean rays go through every part of the lens? Okay. And isn't this a nice one over here? If you instead cover each third with a red, green, and blue filter, will the image appear white? And the answer is, ends with a P, right? Yep. Okay. And what happens if the red is blocked? Then what are you going to see? Blue and green will give what? Bluish green. And we call that cyan, right? Or what happens if you block the green? Then you get the blue and the red, and that'll be bluish red. What do we call that? Magenta. And what happens if you block the blue? Then you'll get red and green, and red and green mixed together. Everyone's obviously yellow, right? Not so obvious. But a nice color addition demo. Bruce and I were having a little conversation, might as well share it. Why is it that you can't heat a bar of metal up until it turns green hot, which is a related question? If I take a bar of metal and I go in a dark room and I heat it, it's glowing all the time, isn't it? But if you can't see the glow, because a rattlesnake might see if you rub it with your hand, make it warm. Rattlesnake can see in the IR, we can't. But if I wrap some wire around it and heat it up, electrify it, it'll glow, start to grow red hot, won't it? And if I continue to increase the temperature, then it will turn to a white hot. And if I increase the temperature, it will melt. But if I could keep the material together, I think we talked about this before, it would finally turn a blue hot. Question is, why won't it appear a green hot? You'll never heat up a piece of metal until it incandescently turns green. Or when you do, it won't look green. And why won't it look green? Check your neighbor. Can anyone name a familiar object that indeed is glowing green hot? Yellow green hot?
Sun.
The sun. The sun is glowing a yellow green hot. When you look at the sun, you say, son of a gun, it's white to me. And why does it look white? It's glowing the green. And if you could take a piece of metal and heat it up, and so the peak frequency would be indeed green. But you look at it and say, well, it looks white to me. Now, why does it look white? Because we're all broad-minded. If we were narrow-minded, we might look at this curve as if it were like this. If something glowed like that, whoo, fat chance. All those vibes would all be just exactly about the same rate of vibration. There wouldn't be a mixture. Then you'd probably get green hot. So very narrow-mindedly, you would see green hot things as green. But what happens when you see the green? What are you also seeing? The red and the blue. So mix it all together, what do you got? Honey, the green ain't there anymore. It's smudged out. And so what looked to be green hot looks to you to be white hot because there's a wide distribution of frequencies. And when you see something red hot, that means it must be glowing over in here somewhere. Say in the IR, in the infrared. And there is some amount that'll tickle the red cone in your eye. So you'll see something glowing a red hot. You increase the temperature, now it's up to here. Increase it even more, and you might get into something like this. And now that's in the ultraviolet. You can't see it, but you can see those lower frequencies of that distribution, and those look to you to be blue. Now, really heat it up. Be invisible. Now you get an X-ray emitter. That's hot. You don't see it. There's not enough that will come down and tickle the visible part of the spectrum. So, hence, why you don't see the green hot. You won't see green hot stars in the sky. You look in the sky, you see white stars. But women will see the blues and the reds more than the men. They will. But the red, white, and blue. Patriotic. Below the border.
Yes.
Yeah. And you take a time exposure, you can get it. Put a camera down, open the lens, and let it go. You see red, white, and blue stars. No greens. Are the green ones there? Yeah, but they look white. Because you can't have the green without also activating the blue and the red.